Okay, welcome to our next video on polymers. In this video, we'll be characterizing length and molecular weight aspects of polymers. So we learned last time that polymers can be represented by a repeating set of units called mers. And in an example like on screen here, we have 6 of those mers as reflected through what we call the degree of polymerization. So there's a dP value of 6, and we see 6 of those mers present here. And we see N groups corresponding to hydrogens. And so for this very short polyethylene chain, we could further draw the structure as such, indicating the degree of polymerization of 6 in this case, and show those N groups as hydrogens. And we understand it from the organic chemistry that every kink in the structure represents a carbon with saturated hydrogens. So we know that at this site there is a carbon and 2 hydrogens, and likewise here. So by this approach, these two structures are analogous. Okay, so we can start to ask more questions here about the overall length of the polymer given its degree of polymerization. So here's an inspection of the sort of sphere representation of atoms for our polyethylene, and we'll recall that all the carbon atoms in that structure were sp3 hybridized, meaning there should be tetrahedral geometry at each carbon center, and therefore a 109.5 degree angle between carbon-carbon units at every site. And so with that geometry, we can start to ask questions. If we could extend this molecule and respect the geometry that we know is present at every carbon, what is the overall length, the chain extended length of this molecule? And so it becomes an interesting geometric parameter or question, geometry question, provided we know the length of the carbon-carbon bond. So if we can look this up, for example, we'll see the carbon-carbon bond is typically 0.154 nanometers. And if we know the overall number of bonds or repeat unit information, then we can add up through a trigonometry approach these lengths here multiplied through by the number of bonds present from end of the chain to the other end of the chain. Okay, so let me just clean that up so we can see some of the other content on this slide. Okay, good. So we see that the carbon molecules don't line up in a straight backbone, but rather adopt that sawtooth pattern owing to the sp3 hybridization at each carbon. And to better quantify this, we show now the equation here for the extended chain length L sub ext. And we see that that is a function of trigonometric kind of parameter here, which we see has the built-in bond angle of 109.5. We saw that we needed to divide that by 2 because we were going to count bonds here. So clearly that angle we only need about half of it to represent that overall wedge. Okay, so only need about half of that angle. That explains the argument inside the sign piece of this right-hand side of the equation. Then we have M, the number of bonds present. Okay, so if we had a way of counting all the number of bonds from head group to head group, we would have the definition and the count for M. And then we need to know the length of the bond in question. And so that's where we turn to tables like you have in table 2.2, and we can see the bond length values for lots of different bonds. So here we see the carbon-carbon single bond present in polyethylene, and we see that value is in fact the 0.154 nanometers that we referred to earlier. We'll note here that in polyethylene, we noticed earlier that the polyethylene repeat unit was defined as such, for example. And so the number of bonds inside the parentheses, we have here a half a bond. Here we have another half a bond. And of course we have a full bond right in the middle. Okay, so there are 2 bonds per repeat unit in the polyethylene, and so many of the simple chain growth, vinylic or carbon-carbon double bond afforded polymers that we've considered have 2N as the value for the number of bonds from head group to head group. Okay, so we can consider modifying the above equation there if we know something about and we want to include something about the degree of polymerization in the equation. So simply said, M in our equation above could be substituted for 2N if we know the degree of polymerization, and that the number of bonds in the parentheses does in fact count up to 2. Okay, so in other words, the sum of those circled values corresponds to the 2 here. Okay, so here you see example polymers that we've seen before where this equation would apply. Okay, so this is for the hypothetical linear extended chain length where we've respected bond lengths and the geometry that we know for a tetrahedral carbon center in an sp3 hybridized carbon in a main chain. In reality, due to disorder and the overall flexibility of many of these bonds, we know that the hydrocarbon polymer, like polyethylene, will often adopt a random coil conformation in its amorphous state. So this overall length in the extended model is more of a hypothetical model because we have not respected the option to bend and twist at these carbon-carbon single bonds. And so to represent now the size of the chain, we might again look to feature distance in the chain. So again, we could look from head group to head group and use an average equation to describe the average distance between these 2 head group pieces. Okay, so we'll see here that we describe that length L as a root mean squared average because it's capturing the overall average distance that will be found for all the different conformations that lead to some distance between those 2 ends of the chain. Okay, so there's the root mean squared average length of the chain now, which is now respecting things like disorder and bond twisting and bending. And here we see again the number of bonds comes into the equation, so we see that as a square root now, and we're going to multiply again by the bond length that we had from our table of information. So in the case of polyethylene, this was the 0.154 nanometers for the carbon-carbon single bond. Okay, and M would be the number of bonds in the kinked structure. Okay, let's just clean that up because we have some more content on this slide. Very good. And so this random walk, as it's called, is describing an atomistic migration in which the direction of each step of the randomly selected units from the chain exist in all possible orientations as permitted by twisting and rotation of certain bonds. Okay, and then we saw this equation. It defines a separation distance from the beginning to the end of this long chain now, and we've called that the root mean squared length. And we see that it goes, the root mean squared length value here on average goes with the number of bonds to the power of a half, or a square root in M as a value there. And of course we need a prefactor there that is the length of the bond in question, representing all the bonds that separate N group from N group. Okay, good. So if you hadn't seen it before, again, we are in this model, we're respecting the idea that we have rotatable bonds, and that's what's going to lead to the random walk concept that we have in our model here. Okay, and we've seen this table before, and now we see its utility again for the random walk root mean squared length approach to estimating the length of a molecule. Okay, so again, these values would be needed here. Okay, so let's take a look at an example here. Here's an example where we have polyethylene, which has an average degree of polymerization. This is the N value we've seen. It's got a value of 750. And we are asked, what is the coiled length? So the random walk model is to apply in answering part A. And in part B, we're asked to determine the extended length of the average molecule if we were able to extend it into a perfectly linear version, still having the bond angle 109.5 at play. Okay, so take a minute to think and maybe apply the earlier equations from the slide to help us with that, and resume the video here when you've had a chance to answer both of these questions. Okay, so in attempting to answer A, hopefully you were reminded that we have the root mean squared length, adapting a random walk approach to determining a coiled length. And this was going to be equal to the L value of the bond times root M, the number of bonds present. We saw that this is polyethylene, so we recognize that there are 2 bonds within the parentheses, and we have N repeat units. So this equation can therefore modify to become root 2N, where the 2 here is the sum of the number of bonds in the parentheses that we see here in the polyethylene example. Okay. So substituting in some parameters from our table, we saw a moment ago that the carbon-carbon single bond length, so this thing, that bond right there is 0.154 nanometers. So that's the value of L. We know that the degree of polymerization, the N value here, is now equal to 750. And that gives us enough information to answer the question. So the answer here is going to be 0.154 nanometers for every bond times the square root of 2 times the 750 degree of polymerization. Notice that we only have units from the first coefficient out front, nothing from within the parentheses. And so we end up with a value here that is going to be in nanometers, therefore. And you should get about 5.96 nanometers for this part A. Okay, let's make some room to answer part B now. Okay, so in attempting to answer part B, we want to determine the extended length of the average molecule represented by this polyethylene with a degree of polymerization of 750. So here we'll use our other equation. The L sub ext is going to equal 2n. We're using the substitute from what you saw a moment ago. So that was formerly m, but we've installed the 2n by the same logic that we just did in part A. And that's going to be times the sine of the bond angle, so that's 109.5 degrees divided through by 2. Be careful using your degrees. Make sure your calculator's on the degree function rather than radians or grades. And we can substitute in some of the same values. So 750 for the degree of polymerization, 2 out front, and then we have the sine of that same fractional amount of 109.5 degrees. Okay, so solving for this, you should get an answer of about 189 nanometers for part B. Okay, so to remind you, that's the extended molar, 189 nanometers. However, when we adopt the random walk, we just calculated a moment ago that 5.96 nanometers was the answer in A. Notice the vast difference here between a more linearized version of the chain where we still allow tetrahedral centers to be respected, so going from head group to head group and linearizing the molecule as best we can without breaking bond angle understandings, was almost 190 nanometers. However, when we adopt the random walk conformation for that chain, more representative of what it would be found in a true application of the material, we see that that chain is only occupying an end group to end group distance of about 6 nanometers. Vast difference there, the two models. So in other words, the coil is this linear chain ends up rather coiled and folding and twisting on itself many, many times to shrink the average chain distance down significantly. Okay, very good. So there's the answers there again, formalized a little more cleanly for you if you weren't able to read any of my notes on the previous